Thank you. So sorry. So first, of course, I want to thank the organizers. That it's a quite original format. I mean, with many different topics, and I hope I learned many things during this workshop. So basically, I'm going to talk. I'm not going to. I hesitated in between talking about turbulence, but maybe I think that either the turbulent people here will know exactly what I will be talking about, and certainly I will not be able to give lectures to those who don't know turbulence. So I decided to talk on a more recent topic that is basically something which is under development. So I will give you some preliminary things, and it's mainly the topic of the postdoc of Chiara Kalashibeta, who is starting in January. So you see, I mean, it's very preliminary. But still, it's also some work by Zakaria Al-Khiati, who just finished his PhD, so working also on this kind of machine learning problems. And it's the subject of a collaboration with Laetitia Giraldi, who is a researcher at INRIA in Nice. So basically, the motivation of this project is the following: is to try to understand how to control in an optimal manner micro robots which are used in medical applications. So it's a topic under development, and it's used in particular to do some very focused drug administration, or to do some microsurgery in a non-invasive manner. So that's the motivation from the INRIA and applied automatic part. And typically, in order to understand the dynamics of such microswimmers, people are thinking in on two different questions. The first question is to try to optimize the locomotion, so the micro scale things on how to optimize the displacement of these micro robots in a very complex environment with possibly some non-Newtonian fluids and things like that, and in particular to find in that case the optimal gate that will lead to a cost-effective displacement. And the second problem is more the problem of navigation. Is that once you have a micro robot somewhere, what you want to do is to optimize the path of this micro robot in order to reach the target. And typically, I mean, these two problems are seen as two different optimization problems. And in the application, the targeted applications in medicine, typically, I mean, these things are happening on the same scale. So the navigation is in a complex environment where typically distances to obstacles, walls, and distances to other swimmers is of the order of the displacement, of the motion, of the deformation done by the micro swimmer in order to advance in the flow. So basically, this is typically the motivations behind that. And so what I want to take into account in some simplified model are three different peculiarities of micro swimmers. So the first thing is that we are in confined environments, so we need to take into account possible interactions with walls. The second thing is that we are going to consider swarms of micro swimmers, so they will interact together, align together. And the third thing is that as it's a small-scale problem, and as there are many things that are not under control, there will be noise in the dynamics. So this, and as you know, I guess everybody of you know, is that the combination of these different effects is leading to some collective behaviors, which can be clogging. So the fact that you can have a kind of traffic jam when you try to go in something which is very confined, or you can get very specific organization in a confined flow, or you can have a coexistence between the different phases. So of course these are not micro robots but chips. So in order to try to describe this complicated physics, I mean, there are different levels of modeling, so which go from something where you try to resolve everything, so including deformation, how the flow surrounding the micro swimmer is modified by the motion, by the deformation of the micro swimmer, and how different micro swimmers will interact in between them, up to things which are very simplified, where typically you can consider active Ising model like systems. And typically, so of course, I mean, in this game, there is a balance between increasing the complexity or decreasing the complexity, and having something which is more realistic in order to fit to applications. So basically, I will consider the simplest case, and so it's a model which was introduced by Perwani and collaborators in the early 2010. So which is a kind of active pot model. So the situation, I mean, the model is the following. So you have a grid. So in our case, we have boundaries on this grid. And basically, and then you have particles which are hopping on this grid, and which are, so it's a single occupancy system, and each particle has a given orientation, so which can be one of the 4 directions on the grid. And then the dynamics is the following. So the particle can swim if there is no neighbor facing the direction of the swim. So this is happening with a given rate, which is a proxy for the swimming speed. Then particles can reorient, so it can reorient randomly if there is no neighbors, and if there are neighbors, it will reorient with a rate which is favoring the fact that they want to align with the neighbors. Okay, and this is involving a parameter which is somehow measuring the balance between random orientation and alignment with the neighbors. And then, of course, so for walls, we are considering the simplest model, which is just bouncing on wall. So if a particle is facing a wall, it will come back with an opposite orientation. So basically, in what we are, so we are considering a channel geometry, so which means that we have 2 walls, top and down, and then we're considering periodic boundary conditions in the other direction. So in this model, we have several parameters. So of course, the swimming speed, the rate at which particles are advancing, the alignment sensitivity, this G, which is measuring how noise is comparable to alignment with neighbors, and then of course we have geometrical parameters which are telling us how confined is our environment, and in particular, so basically, if you can imagine that the grid size is more or less a proxy for the particle size. So it's how many particles we can put in the width of our channel, in the height, I'm sorry, of the channel. So one observes collective behaviors. So of course, it's a completely out of equilibrium system. There is no statistical theory which is well established to describe the different phases that we observe. And depending on the parameters, we can have different behaviors. And in particular, depending both on the density of particles that we put in the system and on the ratio between noise and interactions. So usually one is using the polar order parameter to characterize these different phases, which is defined as the mean orientation, the modulus of the mean orientation, mean vector orientation over all particles. So these are unitary vectors. So you see that when the modulus is 1, it means that all particles have the same orientation, and when the modulus is closer to 0, it means that you're taking random orientation. And so now, if you look at this order parameter as a function of the alignment sensitivity, you can see different phases. A phase where there is no order, where the particles are behaving a bit like a gas, and at very large alignment sensitivity, you have a polar order, which is where particles are forming bands, and in between the two, you have the transition regime, where typically you can see a variety of different patterns in the collective behavior. And so this is the phase diagram, this time as a function of alignment sensitivity and density. So just to illustrate a bit, so when we are in the gas regime, this is typically what we observe in the flow. So what we see is that we have some clusters of particles, but no specific orientation in the distribution. So when we are in the intermediate regime, basically the situation is a bit different. So now these clusters are growing in size, and they start to have sizes which are comparable to the channel height, and possibly, so this is why we call these things clogs, because it can be something which is impeding the displacement of the micro swimmers. And then at higher values of the element sensitivity, so basically after some transients, which can be a bit long and which are longer if you take a wider channel, I mean, all the particles are aligned together and they form a band, and this band configuration is of course always horizontal parallel to the walls. So this is the typical thing. So of course, being in front of a population of specialists of this thing, I wanted to do some comments on the way to describe this on the way to get some hydrodynamic limit and how to use it in order to grab some information. So of course, I'm not I have no diffusion in space. So the situation is a bit different from what people are usually considering. But typically, after doing some heuristic on the coarse graining, what I get is that one can write effective mean field equations for the density of particles with a given orientation, and typically, so it's an advection reaction solution. So where typically you recognize here the form which is due to the exclusion process. So it's this quadratic dependence on the density. And on the right-hand side, you have different rates, which corresponds to the rate at which particles will change orientation, so which are giving some mass exchange between the different orientations. And these rates, I mean, they are nonlinear functions of the densities. So we can use that. So these are some preliminaries to see a bit. So what we can get from this continuous limit. So basically, we can do some linear analysis of different kind of configurations, of course. And so what we do observe is that the uniform distribution is not a fully stable configuration, and in particular, it has the largest eigenvalue of the linearized dynamics is 0, so it's not really stable. So which means that possibly the uniform distribution is never stable, but rather, and this will explain the fact that we observe clusters, so small aggregates. So it's a specific small alignment sensitivity feature. So it's more a gas of cluster than a complete gas. So the second thing is that one can get some upper bound for the stability of the bound solutions, so which are giving us some hint on the values of G that are required in order to get bands, so on the phase transition. But at the moment, we are not able to say whether it should be first or second order. And then the last thing is that by analogy with the Burger's equation, or in the quadratic term that we get in the flux of particles. So basically, one can look at reinterpret the dynamics in terms of shocks, of a sort of Riemann problem associated to these dynamics, and one observes that a front in density is something which is not stable and that will spread this way. And now we are trying to understand if we can formalize better this thing in terms of admissible flux, and in particular on the way one is constructing discontinuous solutions to this kind of quadratic problem. So of course, I mean, so this was just a parenthesis in my talk. So the limitation of this continuous limit is that it's not able to treat the confined geometry that we want to address, because in particular, the limit is obtained by taking very big boxes on which you cause grain. So if you are confined in a region where typically you have a few particle size in the channel height, basically you're not able to use this kind of continuous limit. So back to my problem. So this is typically the variety of patterns that I'm observing. So going from gas, clusters, clogs. So from time to time I can get also obstructions like that, bands or coexistence between different kind of collective patterns. So the question I want to address is whether these patterns are enhancing or impeding the transport of the particles in my channel. And the second thing is, can I predict, monitor, and possibly control these patterns in order to optimize the transport? So the quantity I want to measure is the following flux. So it's the streamwise flux, so in the direction of the channel. And typically it will be the difference between the motion to the right and the motion to the left that I get at large times. And so it will be the rate at which particles are moving in the plus direction. And so now, if I look at this mean flux as a function of the alignment sensitivity, so of course, when I'm below the transition on this part, I have no flux. And as soon as I'm starting to create bands or other patterns, I have a finite flux, which reach a maximum before decreasing. So why is it decreasing? It's because if the band is getting more and more stable, it will be very compact, and the particles will not be able to move because they will always have a neighbor in front of them. So typically, at very large values of the alignment sensitivity, what you expect is to have a zero flux. So now, so basically, what we do observe for values of the sensitivity close to places where we have transport is that typically the transport is always occurring at the edge of the band in a place which is a bit more dilute. And typically, so this is typical, the mean density as a function of the distance to the boundary. And so the band corresponds to having a plateau here, where it's densely, where the particles are compactly distributed. And what you see is that in between the two, you have finite density, but non-vanishing. And when you increase G, this thing is becoming sharper and sharper, going to almost an heavy side. And associated, you see that the flux is maximal close to the boundary of the band. So then, additionally, there are different behaviors. So the first one is dynamical transitions of the band. So here, so green means that the particles are going to the right. So I was starting from a band of particles going to the right, and in the course of time, I'm changing configuration. So I get a clog like that, and then I will be back to a band configuration. But this time, so the red will win, and this time all the particles are red and are then going to the left. So because of this dynamical transition, so the flux is changing sign, plus, minus, and then when we want to optimize a specific transport, which could be, for instance, going to the right, we need to control the formation and the deformation of these bands. So another thing that we observe is that when we are in the intermediate regime, in the transition regime, the statistics are very intermittent and anomalous, and typically what we get is that we have burst in transport. So here you can see the flux. So the flux is the blue line here, and in black you have the other parameter, the polar order parameter. And what you see is that you have fluxes which are bursts of transport, and which are corresponding to some temporary formation of a pattern in the flow. So now that I have more or less described my model, I'm coming to what I want to do. So now what I want to do is to maximize the flux of these particles in a given direction. So for instance, I'm considering that I want to optimize the flux of particles going to the right. And now I want to apply some reinforcement learning procedure in order to control the formation of these patterns that I just described, and to be able to put some bias in having the patterns which will lead to a good flux to the right. And so the framework I'm using is the framework of a partially observable Markov decision process, because I don't want at the moment to give a full information on the state of my system in order to do some control. So what I want is just to have a partial observation. And as it's partially observable, I'm losing the fact that I have a Markovian dynamics once it's projected on these partial observable observations. So the typical framework of reinforcement learning, so I guess this you know it. So typically you have an agent, so which is an operator somewhere, which is observing something from an environment. So the environment is giving a state. Then there is an observation which is a projection of the state. And based on this observation, it's choosing a policy to perform an action. And the learning loop is the following, is that the policy is done, so it's choosing an action. The action is changing the environment, so there is a loop between the agent who is performing the action and the environment which is changed by the fact that there is an action performed. And typically, then in between these two, there is a learning algorithm which is taking into account the action, a reward, which is the thing that is optimized, and the observation in order to update the policy. Okay, so this is the general loop. And so the reward is so as I was telling you, I want things to move to the right, so the reward will be the number of right motions minus the number of left motions that I have in a given time step. So now, when you use this kind of approach, I mean, there are many different ways to represent the actions, the observation, and to learn. And the idea, typically, I mean, and none of them is perfectly tuned for this partially observable Markov decision process, but they are well known for Markov decision process where you have a full Markovian dynamics. In particular, so these are certainly names that you've heard. So now I will show you some results obtained with the simplest approach, which is called Q-learning. So the thing is the following: is that so you try to construct a policy. So what is a policy? Is the action, the probability to choose an action, conditioned on the observation that you're doing. So now, typically, the dynamics is the following. So you start from an observation. You choose through the policy the action that you do, and because of the action, the dynamics is giving you a new observation, and this is the chain of control that you want to find. So now the idea is to optimize this policy in order to maximize what is called the quality value function that is denoted Q, and this is why we have Q learning. So what is it? It's the expectation of the future gain. So typically something connected to your future displacement to the right, which is weighted by some coefficient, some power of a coefficient, so like an exponential decay, which is called the discount rate, which is something which is how far in the future you want to optimize this displacement. And so now so it's a conditional average where it's conditioned on both the observation and the action that you're performing. And so now you get a matrix, I mean, with the different values of omega and alpha that you discretize. So now the idea is to optimize this thing, is to write the Bellman equation, which is associated to this Q matrix, and to have an iterative algorithm in order to converge to the optimal Q matrix. And the policy in that case will be a deterministic policy, which is choosing alpha such that it's the maximal value such that for a given omega, it's maximizing Q of omega and alpha. So of course, in all learning things, you have to do some exploration. So the way we introduce this exploration is by putting some, instead of this max thing, is to put a soft max distribution somehow, which is controlled by an inverse temperature here. So that at the end, we don't always choose the max, but we choose the max with a higher probability, and those with a large value of Q with a significant probability. And then we make this inverse temperature going to infinity in order to converge as a function of learning to the optimal. So now I will shortly tell you what are the states, the actions that we are taking. So we have a very simple model. So our action is either to make all the particles align horizontally or all the particles align vertically. So it's as if we were applying a magnetic field so that the particles were slightly magnetic, and then we say magnetic field this way or this way, and the particles are just aligning. Then so the state for the state, I will go shortly. So the states are this observation of the system that we are doing. So we are losing the mean alignment and something which is, so the mean alignment, which is this polar order parameter, and the average number of neighbors that is telling us how much cluster we are, and then we are discretizing the values of these two other parameters to get 10 possible observations. So just to give you a broad idea, so the things are converging, so we get some policies with this Q-learning, but the policy that we get depend on which phase we are. So in the disordered phase, in this gas phase, typically what we see is that if we look at the flux as a function of time, so in the absence of control, which is the blue curve, so we have fluctuations, small fluctuations, which are centered around zero, and the fact that we control our system now is allowing us to put some bias, some slight skewness in the distribution, where you see that the red values are more likely to be positive than negative. So which means that we are increasing the flux, but with a very slight amount. In the transitional regime, so the situation is a bit different. So in the absence of control, so the blue curve here, what you see is that the flux is going from positive and negative values, jumping and going on almost on plateau, which corresponds to periods where the particles are forming almost bands. So the control case is able to remove this thing by relying mainly on big bursts of transport and giving a significant positive value for the mean transport. And in the ordered phase, so now when you have bands, the situation is again different. So the blue curve corresponds to the absence of control again, and what you see is that we are jumping from positive and negative values, which correspond to bands changing orientation, going from the right to the left, etc. So it's this dynamical transition. And so the presence of a control is now able to remove this change of orientation, so that we are able to keep the band always oriented in the same manner. So again, I think that this is what I'm late, so I will stop here, just to push my slide. Thank you.
Long live India and France friendship.